Welcome to The Explainer. Today, we're diving into a really interesting puzzle in computer science. How can a set of rules, something that looks totally logical to you and me, send a computer program into a total tailspin? We're going to look at the transformations needed to make a programming language's grammar something a machine can actually understand.
So, let's just start with the main question, right? A rule can seem perfectly straightforward, but to a computer, it can be a trap, an endless, inescapable cycle. So why does this happen? And more importantly, how do we fix it? We're going to break this down into 4 key steps. First, we'll get into the parser's dilemma. Then we'll figure out how to tame those wild infinite loops from recursion. After that, we'll clean things up by factoring our rules for clarity. And finally, we'll put it all together into a perfect parser-friendly grammar. So what's really going on here? Well, it's all about translation. We're taking a context-free grammar, which is just a set of rules that are pretty intuitive for us humans, and we need to clean it so a top-down parser can use it. See, that kind of parser has to follow instructions one step at a time, and some rules can just completely confuse it or trap it. We're basically bridging the gap between how we think and how a machine has to operate.
Okay, check this out. On the left, we've got a rule that's super easy for us to read. An A can be an A plus a B, or it can just be a C. Simple, right? But for a parser, this is hostile territory. That first option, the one that says A goes to A plus B, is basically telling the parser, hey, to understand what an A is, you first have to understand what an A is. And boom, that's the start of an infinite loop.
All right, let's tackle our first big challenge, recursion. Now, recursion can be a super powerful tool in grammar. But when it's left recursion, it's like a snake eating its own tail. It creates this vicious cycle that a parser just can't break out of. We've got to tame that beast.
The number one offender here is something called direct left recursion. This happens when a rule for some symbol, let's call it A, starts with that exact same symbol, A. It's public enemy number one because it throws the parser into an immediate, endless loop of trying to define something by using itself as the very first instruction. Take a look at this general formula. You see that A at the very beginning of the first option? That's the trigger. That's what creates the problem. So anytime you see a rule for a symbol that starts with that exact same symbol, that's your giant red flag for direct left recursion. And the solution is actually pretty clever. We're not getting rid of the repetition, we're just reordering it. We rewrite the rule so it starts with a safe, non-recursive option, the beta part. Then we create a new little helper rule, we'll call it A prime, to handle the repeating part, the alpha. This flips the problem from a left recursion to a right recursion, which the parser can handle no problem. Let's see how this works with a classic example from an arithmetic grammar. The rule E to E plus T is a textbook case of left recursion, so we apply our formula. We turn it into 2 new rules. The first one, E to T E prime, starts safely with T. Then the second rule, E prime to plus T E prime or epsilon, handles all the repetition, but it does it on the right side, where the parser won't get stuck. But, sometimes the loop isn't quite so obvious. Indirect left recursion is the sneaky version of this problem. This is where a rule for A might start with B, but then the rule for B turns around and starts with A. It creates a hidden cycle that's just as bad.
To solve this, we kind of have to play detective. Look at these rules. A needs B to get started, and B might need A. To unmask this hidden loop, our strategy is simple, substitution. We're going to take the definition of B and just plug it right into the rule for A. And there it is. The moment we do the substitution, the rule for A becomes A to ABA or CA. And look at that first part. The rule for A now clearly and directly starts with A. We've dragged the hidden problem out into the open, and now it's just direct left recursion, a problem we already know exactly how to solve. So, the beautiful part is, once we've exposed that recursion, we just apply the exact same fix we used before. By turning a tricky, hidden problem into a simple, visible one, we can use our trusty technique to create 2 new, safe rules.
Okay, on to the next challenge. We've dealt with the infinite loops. But what happens when a parser gets to a fork in the road? What if it has 2 or more choices that start with the exact same symbols? How is it supposed to know which path to take? This is a problem of ambiguity. This is where a really useful technique called left factoring comes into play. It's designed specifically to fix this kind of ambiguity. You can think of it like this. If you have 2 street signs that both say, turn left on Main Street to go to, we need to rewrite them to make the first direction totally clear, so the parser doesn't have to guess.
The problem is this common starting part, this alpha. The parser's reading along, it sees alpha, and then it just freezes. It has two perfectly valid ways to go forward, one leading to beta 1 and the other to beta 2, but it has no clue which one to pick yet. That indecision is what we have to get rid of. And the solution is really quite slick. We just factor out that common alpha part, just like you would in algebra. We make a new rule that says, okay, first handle the alpha part. Then a second rule handles the different choices that are left. What we've done is delay the decision, which lets the parser get more information before it has to commit to a path.
Here's a classic example from programming languages, the if-then-else statement. See how both options start with if, e, then, s? That's our common prefix, so we factor it out. We create a new rule for s that handles that common part. Then our new helper rule, s prime, makes the choice. Is there an else s that comes next, or is there nothing? Now the parser has a crystal clear, unambiguous path to follow.
Okay, it's time for the final boss. We know how to fix direct recursion, we know how to find and fix indirect recursion, and we know how to get rid of ambiguity with left factoring. So let's take a single grammar and apply everything we've learned to create a fully cleaned, parser-friendly version from scratch.
This table shows the whole process in one go. On the left, you've got our original arithmetic grammar. In the middle, you can see we've identified that both the E and T rules have direct left recursion. The F rule, though, is totally fine. No problems there. And on the right, you can see the final transformed rules after we've applied our fixes. That's our clean grammar.
And here it is, the result of all our hard work. This set of 5 rules is clean, it's effective, and it's ready for what's called an LL1 parser. It describes the exact same language as our original grammar, but it does it in a way that a computer can execute without any confusion or getting stuck in a loop.
So let's just recap the game plan. You always want to eliminate left recursion first, both the direct and the indirect kind. After that's done, you move on to left factoring to sort out any ambiguity. This cheat sheet right here is your quick reference for spotting and fixing each of these issues. It's a repeatable process for cleaning up any grammar you come across.
You know, this whole process has really been about taking rules that are confusing or cyclical and making them crystal clear. It's all about making sure there is only one possible way to interpret a command. And it really makes you think, doesn't it? Where else, maybe in legal systems or in business logic, or even just in how we talk to each other every day, do these kinds of ambiguous rules create these hidden, cascading problems?